Very good.
Okay, so maybe I'll introduce, given that I forced Markus to do this. So my friend and yours, Markus Land, is going to talk about the K-theory of pullbacks.
Thank you very much, Oscar, for the invitation and also the possibility to speak. So this is a very recent program that I've been working on with Georg Tamme. It's also in Regensburg. So if you have seen talks of mine, so apparently I like to talk about K-theory and L-theory. So this is a different type of K-theory. It's actually about algebraic K-theory, and pullbacks are actually about pullbacks now. So let me give a brief motivation or introduction, a background situation that's sort of going to be a typical type of theme that will enter the talk for quite some time. So suppose the classical situation. Suppose given the diagram that A prime, B prime. So such diagrams will always be denoted by a star. This is such kind of a diagram. So suppose this is a pullback of discrete rings. Let's say unital, but need not be commutative. So just a pullback of discrete rings, such that the map from B to B prime will be pullback, and map from B to B prime is surjective, and then with that, of course, also the pullback map is surjective. So in other words, you can think about this as saying, i.e., as a map from A to B, sending a two-sided ideal of I isomorphically to some two-sided ideal of J of B, and then A prime is just A of I, and B prime is B of J. Okay, so this is what's called a Miller square. And I will typically abbreviate these things by n and square. You say so? Anything wrong already? No. Okay, very good. Okay, so associated to this, here's a theorem, which is due to Bas, Duffy, and Miller. Then you get sort of a long-exact sequence in algebraic K groups for these rings. Then you have long-exact sequences that form. My Victoria sequence that starts with K1 of A, and then somehow goes down all the way. And if you're fine with, I guess you're fine with K0, higher K groups are what they are, and lower K groups are sort of constructed inductively, and once so if you know this phenomenon, then this is going to pass to negative degrees anyhow. So wondering about this negative K groups, they just continue forever. And really the theorem of Miller and the other guys was establishing an exact sequence of that form, so a six-term kind of guy. And okay, so this is obviously very helpful. So this is very helpful to calculate negative K groups. This is a Violator's principle. This is always helpful for calculations. And it continues to the negative direction, so it's going to be here, but not for higher K groups. Because it doesn't tell you anything about higher K groups. So partly if you are not as excited about K theory as I'm at the moment, then maybe one of the takeaways is that what we're trying to do is discuss a phenomenon that sort of reconciles the fact that this only continues to the right, and we want to say what happens to the left.
And no mapping from K2, or is it just not exact?
No, so here's a fun fact. So even Swan proves the following, so you can take any functor from, suppose you have a functor, maybe call it K2 for philosophical reasons, from rings to abelian groups. And then there is not going to be any, so there's the theorem of Swan saying there exists no such functor K2 of rings to abelian groups, making this exact. With any map, need not be natural. And the way you prove this is, there's no way of doing anything, as soon as K2 is a functor. The way you prove something like this is that you say, we'll consider a Milnor square of that sort where one of these two maps splits. So the task is to find one such example where this map is not injective. Okay. So this can be worked out. I don't know from the top of my head what it is, but there's no chance of doing anything. And there's going to be a very explicit reason why this holds. And we'll come back to that in some time. But so it's really not, you cannot prove something better, it's a statement you cannot. So just do it like this. And maybe for spoiling reasons, let me just tell you that the actual problem is the symbol B prime. It's just replaced, I mean the theme of the talk is replace B prime by something different. It will not change the sequence in the slow degrees, but it will make sense for the left hand side.
One typical example of such a Milnor square?
A typical example, I mean if you for example, I mean maybe that's not a very nice example, but so if you take any scheme or an affine scheme which has somehow two irreducible components, you can just cover by two closed things. That would be an example. There are examples coming from group rings that I would like to discuss later. So if you have a finite group and you embed it into its maximal order, then somehow the idea generated by the number of elements in the maximal order is also an idea in the integral grouping. So I'll come back to that. Okay, so that's the classical situation. And okay, so with that in mind, what I want to do now is just write down the theorem and then try to explain what the theorem says and then indicate what you can do with it. Oh, this is the wrong thing. So the theorem was that's the theorem here. It says the following. So assume that star is a pullback of E1 ring spectra. So need not be connected, need not be discrete, just any pullback of E1 ring spectra. So then the claim is then there exists, so we call it refined commutative diagram of E1 rings, which looks as follows. So you do what you've done before, but then you end up with a new ring. You construct a new ring, which needs to get a name, and the name is going to be as follows. Okay, so this is supposed to suggest that the new ring you construct actually depends on the full diagram, so every symbol has to appear at some point. And I'll explain this in a moment. So it comes with maps like this. So this is a commutative diagram. I mean, all these things commute. But of course, this is not a pullback in general anymore, right? The big guy is a pullback, so this is a pullback if and only if this map is an equivalence. But you always find a factorization of this diagram of that sort, such that for any so-called localizing invariant, and so I mean I will explain these words in a couple of minutes. So for any localizing invariant, one obtains the induced diagram E A prime and E of A prime times over A B prime C. This is pullback. Okay, so that's the first statement. And moreover, to explain the notation a bit better, so moreover, the underlying just ordinary spectrum of this new ring we construct is equivalent just to the derived tensor product of A modules of A prime and B. And the maps appearing in this name are the canonical ones. So I claim as a diagram of spectra, you can easily guess what all these maps are. So these maps are all easy. This map uses the multiplication of B prime. And so the statement is that on this spectrum you find a ring structure making this the diagram of rings. Okay, so let me give remarks that are supposed to, so we have some time to digest both the statement and the theory in it. So let me first say what a localizing invariant is. Localizing invariant is a functor which starts with the category of stable infinity categories, small stable infinity categories, I denote by cut infinity x. And for ease of notation, let me just take its spectrum value, but you could replace spectrum by any stable category if you wish. And it's something that sends so-called exact sequences to Philo sequences. And for us, an exact sequence is the following. So it's a sequence of stable infinity categories such that, so this is I. So firstly, I is supposed to be fully faithful. So it's an inclusion of a subcategory. Then the composition of P with I should be 0. So notice that's really just a condition. It tells you that pick any object here, send it down there, and ask if it's a 0 object or not. And then, if that's the case, then this category of such stable categories has, you can build push-outs. So there is a canonical map from just B modulo A to C. And you ask this to be an equivalence up to idempotent completions. So which just means take idempotent completions on both sides, and then it's supposed to be an equivalence. Okay, so that's what an exact sequence is for us. And some other people would call a localizing invariant something that further commutes with filter columns, but this is not so relevant for anything that we do. And yeah, so I suggest to just stick to localizing invariants like this. So maybe we want to see examples of such. So K-theory is an example. Maybe homotopy K-theory in a certain variant. So if you have to, maybe you can replace categories that are just stable. So in other words, have mapping spectra by categories whose mapping spectra canonically somehow enrich or are enriched over, say, modules over some E-infinity ring, for example, any discrete thing. So you can look at, so say, some versions of BG categories, for example. So then homotopy K-theory would make sense. You can, for example, also something that's called cyclic K-theory. You can take THH, TC. Maybe I should also say things like Hochschild homology and all sorts of variants you can build out of these, including any sort of localizations of such. For example, we've been particularly interested in chromatic localizations of any of these. These would all yield examples of such localizing invariants. And of course, I should say that how do you evaluate a localizing invariant on a ring? This is just by definition. We evaluate it on its category of perfect modules, where the perfect modules are given by the full stable subcategory of all R modules. All A modules, okay, you have to fix the left or right modules. So let's go with right modules. So you take all right modules over A, which is a stable category, and look at the stable subcategory, which is sort of constructed by A. Anything that's built out of finite columns from A and is closed under retrace. So these are called perfect complexes, and if A happen to be a discrete ring, those are precisely those complexes which you can build or you can realize as really actual chain complexes which are finite length and level-wise finitely generated projected. Okay, so this is how we evaluate an E1 ring on such a localizing invariant, and examples of such, I mean, these are the typical ones. If you know any localizing invariant which is of a significant other feature than these, I'd be happy to know about this. So these are like the canonical things you should think about. Okay, so now we know sort of what a localizing invariant is, and at least for what kind of objects one can hope to apply this theorem. We can not hope to, but actually apply this theorem. And so let me emphasize right away, I want to be very honest about this. So the talk today is going to focus on the fact that for all purposes I'm going to discuss today, we don't really need to understand what this ring is. That's very strange, but I will try to convince you of the fact that this is the case. But nevertheless, I will try to indicate where it comes from. So describing it explicitly seems to be not completely tautological, and I cannot do that in any sort of generality yet. But for what's going to happen today, it doesn't play any role what this ring really is, only the existence and this diagram sort of. And the fact that its underlying spectrum is of that form is the relevant part. Okay, so let me also say that so the ring structure on this ring we have really depends on these primes. So right, the underlying spectrum apparently doesn't. It's just some bimodule tensor product, which only refers to B and A prime as A modules. But the ring structure on this guy actually does. On the other hand, the theorem tells you that if once you evaluate any localizing invariant on this ring, it will again not see the ring structure. Sort of weird, but okay, that's what it is. But one can make this quite explicit. I might come to this at the very end. Okay, so that's what I want to say about this ring structure. And then, of course, in general, here's a warning. Warning in two sides. So in general, A prime tensor over AB does not have a ring structure. So this is the first part where it's sort of a bit weird. And let me emphasize that the theorem will not give you one on this guy, right? You have to make A, B, and A prime be part of a pullback of some sort. And once you have that, then there is a ring structure. This is sort of peculiar. But in general, you don't expect this to have a ring. And in the one case where you do expect this to have a ring, so if all rings are infinity, then so is the tensor product. It's also in infinity. And so it has an underlying E1 ring. Right, you can just forget that it's commutative, take the underlying E1 ring, and this differs from the one we get. So this is different from
Mark, does that really mean infinity? Does the tensor product inherit a ring structure?
You say if it's E2, 2,
So
3,
even you lose one.
yeah.
Yeah, okay. The statement is not
No, I guess
same
you're
as
right.
for these other ones.
But okay, I mean, I wanted to say the most shocking case is if all these rings are commutative and discrete. Then somehow the tensor product is there, and then you can say, okay, well, maybe you don't take the tensor product, you take the derived tensor product. That sort of sounds fine, but the point is still, it's still not the derived tensor product in general. And so it's a different ring, just the underlying thing happens to be the same. So one has to be quite careful about this. If one happened to know that this guy is abstractly E infinity, then you can also show that it coincides with his E infinity tensor product. So if you get a map and underlying know what happens, so you're good. The problem is really finding out when this guy is E infinity, and I can just produce examples by calculations where some sort of invariant, say, Hochschild homology of this will not coincide with the E infinity tensor product, so I mean they cannot be the same. That's just as a warning that this, or maybe as an advertisement to say this ring sort of produces something interesting in the sense that I'm going to explain as applications, but yet it's quite a mysterious object. It's not really easy to grasp what it is. Okay, so before I want to give applications of this theorem or how you use it and come back to this sequence of Müller, Murphy, and Bass, I want to explain roughly how you prove this theorem because it's so easy that you can just do it in a short amount of time. So the proof strategy is as follows. So you start out with the following. You look at perfect complexes on A, and then there is a map to something that I call perfect, or we call perfect complex on A prime, and then there's a symbol which is sort of supposed to denote something like a pullback, and this arrow is telling us that it's what's called a lax pullback. So in here, objects are triples of the form a module over A prime, a module n over B, together not with an equivalence between the base changes, but a map between This is a map from n tensor over a prime and b prime to n tensor over b prime. Those are sort of the objects, and you can do a nice stable infinity category out of such. And the fact that the star is a pullback, this will imply that this is a fully faithful inclusion. So that's where you use that it's a pullback. So it means that it's a fully faithful inclusion. Okay, so you have a nice full subcategory of some stable infinity category, and you already know that you want to prove something about localizing invariants. So let's just take the value quotient. Just say Q, and Q is just the quotient of I. Okay? So we obtain an exact sequence of stable infinity categories. And so the claim is that Q is generated by a single object, and maybe we call this projection, let's give it a name, pi. So it's generated by pi of the object 0, 0. And okay, so this can be used from the theorem of Schwede and Shipley, that the idempotent completion of Q is going to be equivalent to the category of perfect complexes over the endomorphism ring spectrum of that. Maybe let's call this P bar. Okay, so whenever I have a category which is generated by one single object, it's going to be, its idempotent completion is going to be equivalent to perfect complexes on the endomorphisms of this guy. And so we just call this guy A prime. Okay. So how do you get the claim? Why is the claim? Okay, so from this, we only have to observe very little. So there is a short exact sequence in this Lex pullback. So in this Lex pullback, there is a short exact sequence of the form A going to A prime to 0. So this functor sends a module just to, well, you base change to A prime, you base change to B, but if you further base change to B prime, then they become canonically equivalent, so you just record that equivalence as the morphism. And then you can just see that every object in here actually sits inside a short exact sequence where you somehow take B and 0, 0, and the first guy and 0, 0. And the complicatedness of the morphism is really encountered in the way somehow you extend. You can take any such sequence and then you can put another morphism here, such that it becomes a fiber, and this morphism is going to be complicated, but the objects are easy. So you always have a fiber sequence of that sort. But that does the job, because by this observation A, this Lex pullback is generated by generators of this category and this, which are A prime and B by definition. But in the quotient, they become a shift of one another. So it suffices to take one to generate. So this is all you have to do to see that this quotient category is generated by a single object, say the image of B prime, take its endomorphisms, and then to compute that the underlying spectrum is this tensor product, you use some adjunctions. I'm happy to spell this out in detail maybe later. So this is, you just have to write down some formulas. And it's it's not a hard calculation, it's maybe a couple of lines. But it's not very hard to see that the underlying spectrum is the one you want. To identify that all maps are the things you want is sort of annoying. But it's also not really hard. But of course, once you want to identify maps, you have to do something. And of course, you actually have to go through the definition of how you identify these things. But I don't want to do this now. Okay, so this is fine. And then the one thing that's maybe slightly surprising is you use that you take any localizing invariant and you evaluate on this pullback. You just obtain something that will not depend on anything but the two outer terms. Where are we? So it will only depend on this and this. You can think about this roughly as saying that there is a further exact sequence which relates perf A to the Lex pullback whose quotient will be perf B. but they have adjoints. So once you apply a localizing invariant, you will have a sequence that splits, and in spectra these are just additive. So in other words, you can think about this roughly as saying that this is sort of a bundle over perf B with fiber perf A prime. The bundle is twisted, but once you apply A prime, you will not see the twist anymore. It will decompose. Okay, so that's roughly how you can get at this. So then you will obtain a short or a fiber sequence of spectra which relates E of A, E of the sum, and E of this ring. And from that you can sort of extend out and get this pullback. I don't have to worry what the maps exactly are, but since I didn't identify any objects precisely, I won't do this now. Okay, so this is roughly the proof of the theorem. Okay. And let me say that I feel like it's sort of a slight shift of emphasis. So usually if you have a pullback diagram of the form with A, B, A prime, and B prime, you can ask, if you apply K-theory, is this a pullback? And so there are two ways you can go about. You can either ask, take the map from the top left guy to the pullback, is that an equivalence? Or you can take the push out and map to the lower right guy. And typically what has been investigated a lot is this first approach. And the reason why we sort of believe that this is very helpful is that the push out can be described in terms of the invariant on a ring itself, and the relative term is just something which is induced by a ring map. And so there are typical situations where you can make use of this a lot, and K-theory is an example. For example, if you know that a map is sort of very close to being an equivalence, then it will remain so after applying K-theory. So this is the way one can exploit these kinds of
Can you say the whole last sentence once more?
Yes. Okay. Let me maybe write it down. Okay. So maybe just record as a consequence that K of A or E of A to E of E to E of A prime to E of B prime is a pullback. Is going to be implied by the fact that the map of spectra is an equivalence. So this is just a statement about spectra and the map of spectra. Because we know the underlying spectrum of this ring is just this tensor product. The canonical map you get to B prime is just the one you know. If that happens to be an equivalence of E1 rings, then well, you're good. And if it's only close to an equivalence and you sort of know that your invariant will send things that are close to an equivalence to something that remains close to an equivalence, you will also be able to do this. So this is the way we're going to exploit this. And the point is that if you would have rather said, okay, let's take the pullback of this part of the diagram and ask how good is this map, how far is this away from being an equivalence? In general, I believe that you cannot describe this as the E-theory of some ring. So it's more sort of less direct. I mean, you can use less methods maybe to do something about this map, but this map is sort of, it exists before applying E, and so you can do more things with it. Okay, very nice. So let's do some applications of this. Or consequences, or whatever you wish. And so the first one is going to be about just ordinary excision theorems in algebraic K-theory that are mainly due to Suslin and Wodzicki, which have been sort of key or played a crucial role in various aspects of algebraic K-theory, but prominently they appeared when people were dealing with the so-called Karoubi conjecture. If you want to know that the algebraic K-theory of a stable C-star algebra coincides with the topological K-theory, then you have to prove that algebraic K-theory of such guys satisfies excision, because topological K-theory does. And Wodzicki, Suslin, and more people made a lot of work in this direction. I'm going to present a proof of the result of Suslin's using our methods, which is very, very different in flavor. Okay, so let me write down the theorem. So suppose this diagram star is a pullback. All rings are connected and that the map A prime tensor over AB to B prime is a Pi-Naught isomorphism, and to say n-connective for some n greater equals to 1, and let me tell you that by n-connective I mean the fiber is n-connective. By convention for today. Okay, suppose this is the case, then you will obtain that if you apply algebraic K theory to the diagram you started off with, prime, C prime, so this is what's called n-Cartesian. So let me say I either my torus sequence starts with Kn of A. Okay, so that's the numbering convention then. Of course, you can phrase this in terms of some map being somewhat connected, and you have to find the right numbers, but the thing to remember is that if it's n-Cartesian, this Margus type sequence starts with n equals to 1 continuous. Okay. So maybe let's directly record as a consequence. We get this term by us, Murphy and Miller, where because something is a Pi-Naught isomorphism, and we want to show that something holds true with starting where n is 1, so let's check what happens for n equals to 1. So it needs to be 1 connective, that means it's surjection on pi 1. So pi naught iso we've already clarified. Surjection in pi 1 is easy because the situation was that all rings are discrete. So there's nothing to check. And so you get this for free. And there's just nothing to check, you just automatically get what you want and deduce this result. Okay, so let's do more. So here's a fun observation and maybe an exercise in stable homotopy theory. The observation is that if the map A prime tensor over A prime to A prime, which is the multiplication map of A prime, is n connected, then you can deduce that the map A prime from A B to B prime is, okay, so this is slightly unfortunate, but this is how it is. So it's n minus 1 connected and pi n minus 1 iso. That's wrong. So that's what it is. And so that sounds good because we know that, okay, maybe I should not get ahead of myself. And okay, so this holds true if I'm using all rings are connected, but for n equals to infinity, this is true without this assumption. And this is mainly due to the fact that you have something like you have a map which is so and so connective, and if you tensor with a connective spectrum, it remains so and so connective. Whereas if you tensor with a non-connective spectrum, it will not remain such. But if something is an equivalence, it will remain an equivalence if you tensor with anything. Okay, so this is why equivalences are different. Okay, very nice. So you can use this to observe the following. So if all rings are discrete, the condition of the theorem, so this Pi-Naught isomorphism and n connected for some n, so this n connected for some n, connected thing, this is just equivalent, of course, to saying that some tau will vanish. Other for I equals 1 to n minus 1. Okay, so this you just get for free. And using this observation will allow you to deduce the following, namely if, let me first write it down, if for I over the I, okay, so let me denote by I the kernel of the map from A to A prime. And so if we had a Miller square, then you can look at this kernel, this ideal that was part of the Miller square. You can view it as an abstract non-unital ring, and you just add on a unit, so it becomes unital. When Z is augmented canonically over this guy, I mean, you can ask that these Tor groups vanish for I equals 1 to n minus 1. And if that happens, then you can deduce that also the Tor groups I over A or A prime and Z vanish for I equals 1 to n minus 1 if you have any Milnor square where I is the ideal. So you can think about this as saying this is a condition of the sort, that kind of condition for the universal Milnor square with I as an ideal, which is just, how do I write this to Z? This guy mapping to Z, this maps to A, and this maps to A over I. Whenever you have an ideal I, you have such a square, it's a Milnor square, and you can ask something about this Milnor square. Now this observation tells us if this map is so and so connected, then we obtain a result for these two guys, I mean like this relative term, and you can use this by gluing along sort of the other Milnor square to deduce if it holds for this one, then you obtain such a calculation for any Milnor square. In other words, what I want to say is that this is the condition you have to check in order to get excision in K-theory for a specific square. You have a specific Milnor square consisting of some rings, and this is a condition you can check in principle. And its vanishing will tell you how far you can go with the Milnor, with this Milnor sequence. And what Suslin observed is that if you show something for the universal Milnor square, so just something that only depends on the ideal, then you also obtain excision. So the consequence is that if this holds, then one has my Victorious sequence in K-theory for this square A, B, A prime, B prime, up to degree n, which is also what our theorem tells you. But you don't have to have it sort of, I mean, it just doesn't have to hold for this ideal in general if you just want to know it for a specific Milnor square. And the condition you have to check is this. And there is sort of a global condition you can check which ensures that this condition holds for Milnor squares with a fixed ideal I. And this is Suslin's theorem. This is precisely this condition. If you have such a vanishing, then you obtain a Milnor sequence in algebraic K-theory for any square whose ideal is I. Okay? So this is one way you can use our theorem to reproduce this theorem of Suslin about excision. And let me briefly mention, I mean, the way he proves it is really very much in favor of calculation. So you think about these K groups in terms of EGL plus, which is fine, and then it's a calculation about group homology of these ideals. It's really an actual calculation of group homology. And so far, the fact that you can write algebraic K-theory in terms of a VGL R plus, or in terms of the plus construction, enters precisely for something that says, I mean, so maybe I should explicitly say this at some point. So what we use, that if A to B in general is a ring map, connective rings, and which is a prime of iso, and n connective, then algebraic K-theory of A to algebraic K-theory of B is n plus 1. And you can make versions with coefficients, and all these hold true in the sense. And this is a very classical result, which you prove by using the plus construction, and it is all that enters in for these types of results, which are always of the form, we want to deduce that this map has a certain connectivity, so we can deduce from this Milnor long-exact sequence where you have this ring, something about where you replace it by prime. This is really where this connectivity assumption only enters. Okay, so let me say a couple of situations where this also enters. So this theorem applies in more cases. So let me just briefly mention these. So for example, if you have an affine Misnevich cover, so if you think about discrete rings which are commutative as affine schemes, then a pullback is going to be given will correspond to a diagram of schemes, and if the associated diagram of schemes is what's called an affine Misnevich cover, then you deduce a long exact sequence which is due to Thomas and Trouble. Due to Thomas and that, but it's in the table. So I mean, this sort of, so to say, says that on affine schemes you see Misnevich descent for K-theory, and it just has to do with the fact that in this specific situation you want to check that some map is in equivalence, but it just turns out that the pi-naught condition is for free. It's sort of saying that something covers your scheme. This is the pi-naught condition, and the rest comes from the fact that certain maps are flat. In this Misnevich thing, you know, you have open and entire maps; these are flat. So this derived tensor product turns out to be discrete, but you have a pi-naught iso, so there's nothing to do. Okay, so you get things that are of that sort. You get things that are called analytic. So if F from A to B is an analytic isomorphism along what's called along S, and S is a set of central elements of A that are sent to a set of central elements in B, such that F induces an isomorphism on both the kernel of multiplication with S and on co-kernel of multiplication with S. Isomorphisms, these are isos of this kernel of multiplication with S. And A prime is just a localization. B prime likewise is a localization of B. Then you obtain a long exact Major sequence of what are called analytic isomorphisms. I don't really know why these are called analytic. But you can tell me. So you obtain again a long exact sequence. And this is due to Karoubi, Quinn, and Vaughn. So that's also known, and it's a case, again, it's a similar flavor. So a pi-naught condition is going to be satisfied, so to say, automatically, and then, I mean, you have localizations, these are again flat. So this derived tensor product is just discrete, and you obtain what you wanted. Okay, so this is a situation where it enters in the dime. To say anything more. Yeah, maybe the general, maybe nice case is to say F from A to B would call it Tor-unital, which just means that B tensor over AB to B is an equivalence. Then you can use this observation, which said that then also the map A prime tensor AB to B prime is an equivalence. So for Tor-unital maps and a pullback diagram where the map F from A to B is Tor-unital, you also obtain non-exact sequences. So that was, I think in this language at least, worked out by Tamme in the previous version about excision on K-theory. And you can think about the statement of Suslin. I mean, if you don't care about all these bounds with an n explicitly, you can say that an ideal is called Tor-unital. So I, ideal A is Tor-unital if the augmentation map is Tor-unital in this sense. This was a vanishing on Tor condition, which just says that this map is, this multiplication map is an equivalence. And so you can rephrase Suslin's result for some of this global n in terms of saying if you have a Tor-unital ideal, then you have excision in K-theory. And this just holds more generally for any Tor-unital map. So that part was worked out by Tamme. Thank you. Okay, so this is more or less the direct consequences you obtain just by using this very nice fact from algebraic K-theory. And of course you can immediately generalize. So Thomas Nikolaus suggested to me to maybe call it localizing invariant to K-connective if it has the property that for every map of connective rings, which is a pi-naught isomorphism and n-connective. The resulting map will be n plus k connective. So localizing invariance which sort of increases connectivity. And this will just say K-theory is a one connective localizing invariant, and of course the theorem will apply to any such. And for example, THH is zero connective. By the Dundas-Goodwin-McCarthy theorem, TC will be one connective invariance, and whenever you know something about things of this sort, this theorem or this approach will apply. Okay, so let me tell you something about, in this language, infinity connective things. So those are truncating invariants. Okay, so a truncating invariant is the following. So E, a localizing thing, localizing invariant E, call it truncating if following holds. So for all connective E1 rings, A, the canonical map from E of A to E applied to its pi naught. Whenever you have a connective ring, you can just map it to its pi naught. It's a ring homomorphism. So there is a map from E of A to E of pi naught, and you ask this to be an equivalence. Then we call those truncating. Sort of, you can truncate your ring, and you will not see a difference in terms of this invariant. And so examples of this, classical examples are the following three. So you can take, of course, I have to be strictly. So it's derived periodic cyclic homology. So K is a commutative ring containing the rationals. K is a commutative and discrete ring containing the rationals. And so then in this form, this is a result of Goodwin's this paper about Hochschild homology derivations in the free loop space. He essentially proves that derived periodic homology satisfies this condition. So that's a typical example. Then another one is what's called in the literature inf. So inf stands for infinitesimal K-theory, and it's the fiber of a specific trace map which goes from rational K-theory to negative cyclic homology of the rationalized relative to Q. So this is negative cyclic homology. And okay, so this you can read as whenever you have a map of that sort, there's going to be a square consisting of that map in rational K-theory and in rational negative cyclic homology, and the statement is that this square is a pullback diagram. And that's what Goodwin proves in his very first result about this is the Goodwin-Jones churn character, and then this sort of the groundbreaking part of trace invariance proves that this satisfies this truncatedness property. Okay, maybe he made a statement about simplicial rings, but for these rational versions, you can always replace anything by a simplicial ring, and it will really directly apply. I learned that in a paper of Suslin and they explicitly observed that you can always replace A by A tensor HC. This will become a simplicial ring, and it's rationally equivalent to the old guy, and it's a pi-naught iso. So you can use this principle again to deduce that on rational things you can always reduce these cases. And then there is I guess probably nowadays maybe a very famous invariant, the fiber of the cyclotomic trace map from K-theory to TC, which by Matthew Dustin-Clausen and Matthew Morrow is now called A-inf. I don't really know what that stands for, but so that's also a thing. And the fact that this is truncating is really the theorem of Dundas-Goodwin-McCarthy. So they state slightly more. I mean, they in fact prove whenever you have a map of such connective rings, which on pi naught need not be an isomorphism, but quotient by an important idea. So then you get this, but in particular for pi naught isomorphisms, you obtain this theorem. And so maybe you can just collect them. What we believe are very nice properties of these truncating invariants. And so, yeah, okay, maybe I'll first take the theorem and then contemplate on what it says. Okay, so the theorem we can prove about truncating invariance is the following. So we get EV truncating invariant and can star a pullback of pullback and all rings are connected. So I'm making a fuss about this because a pullback of connective rings is not what I want. It's really, I need to have it a pullback in E1 rings, and then if all rings are connected, this is an actual condition. So this is what I want to
That's
say.
just the condition that applying all the two times together.
Exactly. Yes. Precisely. So a Milnor square will always do because already one was subjective. Exactly. So the theorem says that then okay, so there's a couple of points. So then E applied to star to the pullback. So that's what I would like to call excision. And this is like the best form of excision. If you have a pullback diagram in which all rings are connected, and I forgot one condition, so maybe this condition on phi naught we always have to impose, which is automatic for Milnor square. So the surjectivity condition will tell us that type of pi naught is an isomorphism always. But this is a condition, of course, we need. Then the truncating invariant will map this square to a pullback. So then, if you take precisely this situation that I made, so this map is an equivalence whenever I in A is a two-sided nilpotent ideal and in particular A is just a discrete ring. So, in fact, this Milnor good within the McCarthy theorem told us that this holds true, for example, for the fiber of the trace. But it's just a general principle of these truncating invariants whenever you have this pi naught condition, this truncating to the pi naught gives you a pullback, then you can deduce that, and it gives you an equivalence, you can deduce that also further apportioning all the important ideals will not change with that. And the geometric property, maybe that's also quite nice, so E satisfies, it's called CDH descent on scheme S, where S is Noetherian, and this denotes schemes of finite type. SC is finite type. So in other words, really the only missing ingredient for a general localizing invariant to satisfy descent for this CDH topology is showing that it sends an abstract dot square to a pullback square. And so there's been a recent breakthrough by Georg Tamme, Florian Strunk and Moritz Gerst from Regensburg, who proved a version of CDH descent or a pro version of CDH descent for these abstract orders in K-theory, and one can use their methods to deduce an actual CDH descent statement for truncating invariants. And let me just orally briefly explain why one would expect this. The construction they do involves taking derived blowups in the sense that you replace at some point schemes by derived schemes. But somehow by definition, our truncating invariant will not see a difference between derived schemes and underived schemes because it only depends on pi naught. So this is sort of, I think, very philosophically not super surprising that you can get maybe a better statement for these truncating invariants, which doesn't see the pole this pole part. Okay, so I have a couple of minutes left, so let me just prove the first two parts because the third is of a very different flavor. 2 and 3, so we can discuss part 3 if you're interested in private. Okay, so the proof for 1, and there's nothing to do. So you just, well, there's something to do. So apply the main theorem I introduced, and use that E of A prime circle A D prime D to E of D prime is an equivalence by assumption. Phrased like this, it sort of sounds tautological, and the way we set up the proof, it is of course tautological, but I think, for example, in the examples that I've presented before, so from HP, this is a theorem of consequence. I think this was really sort of the groundbreaking game changer in this business when they were able to prove that periodic cyclic homology, they did it for K being a field of characteristic 0, but that this satisfies excision, this was really a game changer in this business. So this is the example we have here. So the KQ inf part was dealt with by Continuous. And again, I guess in K theory or in K theoretic type of excision results, this was again sort of a game changer. At least this is what Lars and Hesselholt always tells me, that really, the ideas of Continuous were the things that really made the essential progress in this world. And for this K invariant, so in the p-adic case, is due to Geisser and Hesselholt. And in the integral case, maybe I should say in the p-adic case for discrete rings as opposed to connectively one rings. Maybe not such a big part. So and in an integral version it was done by Dundas and Kittam. But in the way I presented here, they need some extra technical assumption. So namely, they need not assumption of that sort, but they need both the map from B to B prime and the map from A prime to B prime to be a pi naught isomorph, pi naught surjective. Need both maps. And they were sort of unhappy about this, but for various reasons, due to technical nature, they said, we cannot really get away with less in their proof, but okay, now we can, just using this main theorem. So what these are sort of, these examples were mostly known already and also prominently known. But the way we set it up, it's just sort of a topology. Okay, so let me finish. We have very few minutes to do that. So to prove 2, because I find it very, very fun to see that, this condition really says nothing. This truncate in this condition says nothing for discrete rings. Right? If you apply to discrete rings, it tells you precisely nothing. And so it's sort of surprising that you can get something out of it, at least to me. And so the proof is as follows. So you consider the following diagram. So you take A and A modular I. So you want to prove something about this map. So let's put it into a pullback square where we can say something about the other map. So let me give short names for things, and then tell you what these are. So this is a DGA which is of that sort. So I take I in degree 1, A in degree 0, and I just take the inclusion. And because I is an A module, this is a DGA. So that's fine. So I want to do something similar with this guy, and namely mapping I to A mod I. With a 0 map, there's nothing else we can do. Also sitting in degree 1 and degree 0. And now I want this to be a DGA, so that of course doesn't make sense. I is not an A mod I module, so I have to tell, and I always forget this, that without both generality I squared is I is 0. So it's a nilpotent idea, and by induction you can sort of get down to the case where I squared is 0. But then I is an A mod I module, so I can do this. This is also a DGA. And I wanted to write this down in this way because, of course, this is as a spectrum equivalent to A modulo I. Okay, so that's obvious, but these two maps are different. So this is sort of the, now the maps are the obvious maps. Okay, so now I don't have to say anything. And the observation is that these two maps are not the same. I got a bit confused about this. I thought you just take twice the same map and you take the pullback, it's obvious. But this is of course only going to be the pullback if these are both the same guys and the same map, then this will split if it's a pullback. So, it will only work if it's a split square zero extension. And so you just have to change the map to also get a pullback in the non-split case. Okay, so but now E of that is a pullback. You just have to check these assumptions, but it's not hard to see. This is A mod I, this is A mod I. If you tensor over A, these two remains A mod I, that's also the same pi naught here. You can check the map as an equivalence. So you can apply the theorem, that the main theorem, which tells you this is a pullback. And well, then you can just again see that this is a map of connective rings, which is a Pinot isomorphism, by the way I've constructed. So P applied to this is also an equivalence. And D of the law map. That is an equivalence by the truncated property. And then so also the other things. Okay, so maybe I will finish here, sorry for running over time. Thanks.
Any questions or comments?
Yes.
Was there an algebraic description of the A circle tensor B prime in the case of discrete?
No, I don't think so. It's very peculiar. I mean, I can give an example where I can tell you. So there is a very illuminating example, but it will not be satisfying to understand the ring in general as a ring. But still, the examples may be instructive. So let's consider the example of the following linear square, where take K any commutative ring and any element in K. And then you can do the following, you can snap K to the polynomial ring, two variables, and this is going to be a pullback if I take the polynomial ring in two variables and I divide out the ideal generated by yx minus delta. And so in this case, so this ring, which is now very difficult to write down. Okay, y. This is given by the following ring. So first of all, it's discrete because these maps are flat, and then it turns out to be the ring which has two free non-commuting variables. So this is two non-commuting variables. It's a non-commutative ring. Variables. So the free non-commutative K algebra on two generators modulo the same idea. So maybe that's sort of a nice formula you just pass sort of from the commutative case to the non-commutative case. And so mainly this example is supposed to say, even if all things are discrete and everything is commutative, the ring can get non-commutative. And also, in principle, you can work out what the pi naught of this non-commutative ring is. I mean, in principle. But somehow understanding the higher homotopy, in principle, you can also hope to calculate the homotopy ring, but then understanding the ring spectrum itself is complicated. And what you can do is the following: if this diagram you start out with is one of HK algebras, or of K algebras where K is any E infinity ring, then the resulting ring will also be a K algebra. So you can use that sometimes to make calculations. For example, if you go over the rationals and the thing has homotopy polynomial ring on the generator in degree 2, then this is formal, and the homotopy ring determines the E1 ring. But apart from that, so far I must admit that there's no way for me to really grasp what the actual ring is yet.
You mean what you wrote, so yx
Yes.
and no xy.
Yes.
So over there, the order doesn't matter in there.
Yes.
Okay.
Oh, it's totally.
Fantastic. I can explain it to you, but maybe I should do it. It's fantastic. I don't do calculation at all. And while I'm at it, let me tell you that it's fun to work out also. You can now calculate the K theory, say, of that ring, because you can calculate the K theory of these guys. Say K is regular, for example, then this has the same K theory as K itself. But B, you can also analyze the map from K theory of this guy to K theory of this guy in specific situations. So if I may, I'm just going to do it. So you have to stop me by brute force. So then we obtain a map of that sort. So it's y yx minus 1. So it's the universal non-commutative ring on two variables. I mean, the universal ring in which a specific element is given a left inverse or right inverse. But which is not invertible. And on this side we get the normal polynomial ring. Plus minus 1. So this turns out to be a localization in the non-commutative sense, a co-localization in the non-commutative sense. And if you apply perfect complexes, you can show it that it's going to be sent to a Verdier quotient map. So you can analyze the difference of the K-theory of this and this by means of localization techniques, and it will just turn out beautifully that the algebraic the fundamental theorem of K-theory will give you exactly what you want. But sort of the calculation of the fundamental theorem of algebraic K-theory is essentially the same as analyzing what the file is. So I mean, you don't really get a new proof, but it's a different perspective on the fundamental theorem, and it is actually this particular example was the one we got most confused about in the beginning. Because I mean, you know, this is a Müller square. If you take a normal polynomial ring, and then it just looks like, oh gosh, I mean, what can this ring possibly be other than a polynomial ring in two variables or this normal? Get super confused, and then we worked out that this is the one you get. So then you get quite lucky here. And the other extreme cases where alpha is 0. So then you have the following. This is all the non-commutative coordinate axis, or yx. And this is the commutative two-dimensional coordinate axis, modulo yx. And now it comes very handy that you only divide out yx and not also xy. Because the kernel of this map, so the kernel, this guy is of course generated by yx minus xy in general. But okay, that was already 0. So it's generated by xy. And then you observe that xy squared is 0. Because yx is 0. So you divide out an important idea. This is a square 0 extension, and you can calculate by using trace methods. And let me say, I mean, not directly, but roughly, it is on the nose true that this is the way Hasselhoff calculated the K-theory of the two-dimensional coordinate axis if K is a regular FP algebra. So it just turns out if you calculate the relative TC term for, I mean, TC of that, and then take the relative thing, this is just fully calculated. It's all fun. So I mean, you can make things, at least in this case, sort of explicit, and in other cases only if you're lucky.
Yeah. So this is probably a fair question. Like over a decade ago, Jeff Smith announced like a Myra-Torres thing where you were smashing together ideals instead of rings. Is that a relationship?
Yeah, I don't know. Bob Brunner wrote to me an email 2 days ago asking the same question and saying, I saw your talk. Does it have any relation to, I don't know, are there notes? And so he sent me handwritten notes, but I couldn't really see if there is a direct relationship. It felt to me that what he wanted to do is understand the K-theory of a pushout of the one ring. So it's on the free principle, and this is not what we're doing here. And I couldn't, I mean, from the notes that I saw, I couldn't really see a direct connection, but it would be fun to see if there's more going on. But unfortunately, I don't know yet.
Whoops. Thank Markus again.